Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see how to do the the database compilation. This is basically taking the output from thermodynamic assessment and what to do with that. These are going to be the contents. Uses of the thermodynamic assessment and its output. Basically there are two: assessment of higher order system and extrapolation of data to higher order systems. Then in that case we have to identify what are the subsystems in any higher order system. We'll see about what are these subsystems. Then database compilation, where we need to know this idea of isostructural phases, and then certain compatibility issues we'll see. And when we merge different databases, issues such as new n members can pop in, and certain issues in extrapolation can also appear. We'll see about that. This is a kind of outline of what are the different places where the output of thermodynamic assessment can be used. This picture in the top is something that we are familiar. One side we have model file, one side we have input file, and the par file where the optimization occurs. So these three things we have been doing for the last few classes. What happens is, in the par file, when we are doing the optimization and we see the need for new models, we have to go back, create new models in the TCM file and do the optimization again. Or if we see that some data are required, new data are required to do the optimization better, we have to generate such data and put it into the input file and proceed with the optimization. Once the optimization things are completed, we have this nice optimized parameters v1, v2 and so on. And these things will be kept in a TDB file. Let's say if we do it for a binary, we have done it for AG CU system, silver copper system, we can get an output of TDB file from that. In fact, we have plotted a phase diagram also directly using that. That TDB file can be standalone one for a binary system, or if it is done for a ternary system. Okay, and that can be published as thermodynamic assessment or thermodynamic modeling for so and so binary or ternary separately. CalFAD kind of journals, majority of the papers in the CalFAD journal are dedicated to this sort of assessment work. And what are the other things that can be done with this data that is generated is construction of higher order databases. And other use is assessment of higher order system. Basically, a higher order system will have multiple lower order subsystems in that. And if assessments of all of them are done, they can be taken for the assessment of higher order system. That is another purpose. So these are the things. Thermodynamic assessment is important by itself. Thermodynamic assessment of lower order system is important to assess higher order systems. So this is where the assessment output of lower order systems is useful. That is to do the assessment of higher order system. And then another broader purpose of the assessment is to provide the building blocks of multi-component thermodynamic databases. Okay, these are the commercial things that I have been talking about, where multiple subsystem data are combined to form a multi-component databases. And extrapolation to higher order systems happen here because most of the data is for unary, binary and some ternaries. Let's say 7 component or 12 component kind of systems. For them, again calculation can be done using the extrapolation from this lower order system data. So all lower order subsystems data are compiled into multi-component databases. So when we say subsystems, what are they? We can understand that using this example. Take A, B, C, D, 4 different element quaternary system. It has the following subsystems. How many ternaries are there within this? You can use combinatorics 4C3, which is 4. So ternary combinations we are finding. So 4C3, 4 is the total number of elements we have. So these are the different ternaries we can extract from this: ABC, ABD, ACD and BCD. So these different ternaries can come. And how many binaries? 4C2, 6 binaries, all these combinations of binaries, and obviously 4 unaries, single elements ABCD. Now data of all these subsystems are ideally required to get a reliable extrapolation or thermodynamic assessment of the quaternary system. Okay, only these are enough. We don't need directly 4 component data. With this itself we can predict reasonably well. That's the reason why we are putting this word reliable here. So we can get a reliable prediction of 4 component system data based on this subsystem data. and it is relevant when phases extend, that is isostructural phases. We have seen about extending phases and emergent phases previously. These extending phases are called as isostructural phases, and it has a slightly broader meaning as well. We will see what is that. You see here, isostructural phases are these. If they have the same structure but not the same lattice parameter or chemical composition. Okay, you see here there is a ABC system, and alpha phase is a B-rich solid solution. It is there in this BC binary site. It is also there in the BA binary site, right? And it is there in the ABC ternary space as well. Okay? That means this alpha is extending from this binary site here or this binary site here. Eventually it is also meeting, and people say this is a continuous field from one binary to the other binary, which is basically a extending phase. Similarly beta and liquid also. This B2, if you see, B2 phase is there in the AC side. It is also there in the BC side. It is also continuous from AC side to BC side. Okay. And there is a tight triangle here. All the dark regions are two-phase regions. Okay. Blue things are single-phase regions. That's how it is marked. So this phase is extending. The solid solutions or liquid solution extending is quite frequently we can see this kind of thing happening in multiple systems. But intermediary phases, these kind of things also can extend. Even if they are not continuous, this B2 here and the B2 here can be same structured. They are isostructural phases. The moment you see isostructural phases, there is a high chance that you get some kind of a continuous field like this, or at least significantly extended fields like this. Okay. So all these phases, alpha, beta, liquid and B2 are these isostructural phases. They appear in multiple systems with the same structure but different chemical composition and different lattice parameters. So this is one thing that we need to be careful about. You see CRSI, FESI, MNSI. In these three systems, an M3M stands for some metallic element, either chromium or iron or a manganese. So M stands for that. M3Si phase exists in these systems. So you would think that since silicon is common, possibly silicon forms this M3Si phase with all these things with the same crystal structure. But that's not true. You see, Fe3Si and Mn3Si are isostructural, but Cr3Si is not. Okay. How do we know this? We have to check structure-baric notation. It's a very nuanced crystallographic notation, and there are sources for this. This particular source has a very beautifully compiled or very easy to navigate kind of website where you can find various structure-baric notation for several compounds. But note that structure-baric notation doesn't exist for all the compounds. So that's the care you need to practice when you are identifying isostructural phases. Now we will see compatibility issues. One compatibility issue can be from unary descriptions. For example, you take these complex phases such as Laves phase. One often has sublattice formulations that involve unary functions that are not part of SGTE recommendation. You see, SGTE gives Gibbs energies for different crystal structure for the same element, right? So, but it doesn't give for all the crystal structures. For example, Laves phase crystal structure. For that, for each element you don't have the SGTE data. So we don't have the standard data for this kind of unary phases. In that case, one has to use non-standard values, and that can cause problems. Then another compatibility issue is model level compatibility, where this thing can happen when combining two assessments. It is essential that a phase that forms or may form a continuous solution from one binary system to another, like the B2 that we have seen as isostructural phase. Binary phases extending or meeting in a ternary regime, that is described with the same model in both the assessments. Okay? You take the example of same B2 in two different binaries. Okay, let's say Al-Ni aluminum nickel forms a B2, and some other phase, let's say cobalt aluminum also forms a B2, and these two things are there. For these two B2 phases, separately in aluminum cobalt and aluminum nickel assessment, some model will be used, sublattice formalism model will be used. The same thing should be used when aluminum, nickel, cobalt, ternary is assessed. Okay, let's say for aluminum, nickel and aluminum, cobalt, assessments are reported and the sublattices are different. Then one has to do the assessment for this binary again. At least one of the binaries should be assessed again with the model that is compatible. And this is a challenge. Okay, so this is the care we need to take. Select models that are compatible with the systems to which the assessment results shall be combined later. And this has to be kept in mind. Then when merging multiple data, another issue can come, that is creation of new n members. For example, in FE-CR binary, we have this FCC model. FE and CR both are in single sublattice. Let's say vacancy is not taken. In iron carbon binary for FCC, iron is taken in one sublattice and carbon and vacancies come in the second sublattice. You have seen about interstitial solid solutions, how they are modeled in sublattice formalism. This is how they are modeled. Now, if you want a merged description, FEC or C we are looking for, ternary. For that, how the FCC will be modeled? FECR, both the substitutional elements will go into this sublattice, and carbon interstitial element is going to be there, so that has to come here. If you put it like this and start writing the constituent arrays, then we will be seeing new n member CRC, isn't it? CR in first sublattice, carbon in second sublattice. But it doesn't appear in reality. Such n members can be fictitious and hence problematic because we don't have experimental data for this. So carbon in interstitial size of chromium, that kind of phase is not there. We don't have experimental data for that. So we cannot get a reliable experimental input for that to do the assessment. So this can be problematic. So this kind of n members, new n members will appear as we go to higher and higher order. You think about it. If you take a 7 component or 13 component system, how many binary ternary will be combined? And in that, if you start merging them together in this kind of sublattice, then you will be ending up getting multiple new n members which may not be there in reality, and there cannot be a way to get the experimental input for that. Okay. By default, model parameters for such cases are treated as 0 because these n members for which if the assessment is not going to be done, that will be taken as 0. But that may not be the right thing depending on which system where this is taken as 0. Okay, but it might cause problems depending on the system. One more thing about this merging is order disorder system, where suggested model is partition the disordered and ordered parts. Okay, so that makes it easier to merge across different system where disordered part only can be available. You see A2, which is BCC in structure-metric notation, and B2 is ordered structure, looks like a BCC. Okay, A2 B2 order disordered transformation occurs in some systems, but only disordered phase BCC occurs in many systems. For example, if you take ALNI, B2 phase exists in that, and that can be combined with A2 phase, the normal BCC phase, in the CRNI system. CRNI doesn't have a B2, it has only BCC. Okay, these two things can be merged, provided we have this partition of disordered and ordered parts separately in the model itself. Okay, in extrapolation there can be some issues. A poorly assessed binary may not be reliable on extrapolation to ternary. Why? Because of this insufficient input data for the binary assessment. So binary assessment doesn't have a lot of points. It is very scarce points are available and somehow fitting is done. And the fitting can be done with different sets of parameters also. All of them can reproduce this experimental scattered points. But will they be able to do the extrapolation right? That's where the problem comes. When we saw the guidelines for optimization, there we said extrapolation ability can be checked. That is, if there is a range over which experimental data is available, temperature range, plot a phase diagram for a wider range and see how good it is. Okay, the same thing can be applied here as well. To higher order system, if you extrapolate, can the models work well? Okay. Many sets of model parameters can reproduce the available data. The data is anyway insufficient, we say, okay, in a binary system with equal accuracy. But these parameters will give different extrapolations into ternary systems. So one has to be careful with this. In the compiled databases, there can be issues. Certain new phases may appear as stable phases where they should not. Once you plot the phase diagram, you will know. And certain stable phases may also become absent. These kind of issues can pop up. So cross verification and validation is important. Even experimental validation can be done at a higher order. Few experimental data points can be chosen and verified. And finally, one of the most important things about databases is databases made for a family of alloys. This is what are commercially sold. Thermodynamic databases that include only a limited number of ternary assessments focused around a base element such as iron can provide reliable extrapolations to multi-component alloys built on that element. If such a database is built, then this is easier. These databases are extremely useful for guiding new experimental studies in alloy development within that family. Because we can choose some compositions which are promising just by doing their calculations and then go for focused experiments. Okay. Since carrying out detailed experiments on multi-component systems for very multiple compositions is often very costly. Okay. So one such database is TCFE, Thermocalc Iron Database. This is used for developing new steels and all. And PanFE is from PanDat. And the nickel-based superalloy, that is TCNI database. These are commercial, multi-component, internally consistent databases. They're quite accurate. I sometimes feel quite fortunate to be here that this point in time that so much of thermodynamics that has been done over a couple of centuries, so much of experimental data, wealth of data experimentally very carefully done, and those things are taken and put into this kind of computational tools, compiled into databases, and be able to predict about new different materials, their behaviors, the phases that can form in that, predict the microstructure. I think this is such a wonderful thing to do. And of course, there is a lot of scope to improve also. It's also quite challenging in that sense and feels like it's a worthy of a challenge to take up. Thank you. I hope the lecture is useful. See you in the next class.